idea what is the benefit? Exactly, yeah. We need it for the design the controller. So we discussed about the part transformation. We said that if we transfer the system from ABC to DQ, then we can make the controller easier and more flexible. You can actually use for different application. So now I'm going to transfer this three-phase system to part transformation to see that, is it really true that if we transfer this one from ABC to ODQ, then it makes our life much more easier if we are going to design the controller or not. So, so for this case, we get back to the part transformation system. We design here, we discuss about this one, and we see that, we can use this matrix for the DQ or for the reverse one. So now we are going to get back to dynamic model. We obtain for the system and then this one and transfer it to DQ. So if we get back for three-phase definition we had, it was like this. di to dt is equal to minus r over to L I ka minus 1 over L dn ka VDC plus V ka over to L. Okay? Now we are going to actually transfer it to three-phase. So, does anybody know that how we can go from ABC to DQ? Part transformation, but how? We should transfer all of them one by one. So for the first phase, so this is something that we have from the matrix. So first phase is the cosine omega t times to ud minus sine omega t times to uq plus 1 times to u0. So U can be actually voltage or current, doesn't matter. Or, I don't know, switching state function, anything you want to transfer. And U2 is also the same, U3 is the same. So we start by first phase. From here, so it is also very easy, but if you don't pay attention 100%, you will not get the point very well. So, based on the equation, this matrix U1 is equal to UD cosine omega t minus UQ sine omega t sine omega t plus 0. Okay? Do you agree? And what is the omega t? Angle of frequency. I need a complete answer. What? Page? Page of what? Omega t. What is the omega t? Okay, but from where? From where? From where is coming? I mean, assuming that I'm going to program this one. No. No. Between V and D, normally we have 90 degree. It's constant. No, but what is the omega t? You can say that this is 2pft. You can see that this is the, I don't know, frequency of the sky. You can see, but give me complete answer. And give me the reason for that one. Angle of what? Okay, you say, but you don't give the complete answer. Yes.
Omega is the angular frequency of the
Great. Okay.
Omega is the angular frequency of the voltage or current, whatever we are using. And
Okay.
T is the time that we have.
No. My question is that what is omega t?
Angular.
But from where is coming? I know that but this angle is coming from where? From where? PLL. PLL measured something and then give the omega t. Okay? So this something is coming from where? From grid. I mean, no, it's coming from grid. Yeah, because we are going to synchronize with the grid. So if we put this one, omega t, from somewhere else, it means that we are transferring our dynamic model to the angle of something else. Okay, so we are going to be integrated from the grid. So if we get back to here, to this model, we get V1, V2, V3 as the input to PLL. Then we get the omega t as the output. Then this omega t from the grid is used for the control design. Why? Because we are going to be synchronized with the grid. It means that when we provide the current or voltage actually for the grid, it should be synchronized to support the grid. And if you don't consider that one, it makes a disturbance. Your converter actually react as a source of pollution, not a source of actually energy for provision of the supportive functionality for the grid. So this is the problem, and this is very important that you consider any omega t you consider for this Park transformation, transfer your dynamic model to that atmosphere. Okay, so it is very important you consider this one seriously. So then we get back to again to U1. From here, this matrix, we have U1 is cosine omega t, UD times the cosine omega t minus UQ times the sinus omega t plus U0. So now our U can be IK. Do you like it? Because we can transfer all of these things. So L is a constant value. So we don't need, we just multiply to multiply it by di to dt. So we don't need to convert it. But di to dt is, and IK is, DNK is, VDC is not, VK is needed to change because they are a variable, they are not constant. So then now for the U2 and U3 also we follow this UD times to cosine omega t minus 120 degree, UQ times to minus sine omega t, and we see that we have also 3 equations here for that. Okay? I forgot your name again. Krudika. Okay. We have 2 problems. One is a hard name for me, and then you are actually Krudika. Like this. Krudika. You're sleepy, yeah? Yeah. Is it boring for you? Is it boring for you? You feel sleepy? Ah, you were the same team with them, so you didn't sleep well. Okay, good. If you want, if you get tired, we can stop it here. But if you, Udaya, Should I continue or continue? Okay, okay. So now in phase 1, L di to dt plus Ri plus dn vdc is equal to V1. So L di to dt, L di to dt. L is constant, di to dt. di is cosine omega t minus iq sine omega t plus I0. Okay? We wrote based on the I. It was U, now is I. So, di to dt. So is di d to dt cosine omega t minus id omega sine omega t. Do you agree for this? Yeah. F times 2 jt is f prime g plus g prime f. Okay? So, this is this part. Okay? And then we have another part, minus. So, f diq to dt sine omega t minus iq omega cosine omega t. So is this part. And plus di0 to dt. Is it clear? Yeah. So the first part we have also L di to dt. So L di to dt. L and L. Sorry. It cover all. Yeah? So second part. Ri. R times 2. Id cosine omega t minus iq sine omega t plus I0. Yeah? Is this part. So now we cover this part and this part. And we now is in dn1 vdc. Vdc is a constant value. So, but we consider dn is equal to dn1 is d cosine omega t or dnd minus dnq sine omega t plus dn0. Okay? So we had VDC times 2 VDC. Yeah? Siddhant? Is it still clear or? Yes? Okay, good. Thanks for confirmation. So we have also here. And then now we jump to V. V1 is equal to Vd cosine omega t minus Vq sine omega t plus V0. Okay? So look at here. We have this part. Is it like this? This part is this. This part is this. And equal to this part. Okay? So, Rakesh, is clear for you? What are you writing? But I give the slide to you. Okay? So this material also I sent to Udaya and can share with you. Okay. So any questions so far? No. Easy like a piece of cake. Okay, good. What?
In some cases, we are going to consider V naught is 0.
Hmm?
VD, VQ and V naught. V
Hmm?
naught is 0. But here we can consider it as a 0 or in unbalanced system.
I mean, basically, if this depend on what kind of actually system do you have, but we mentioned because this is the balance system, we can actually ignore that one.
If it is unbalanced, how we are going to calculate?
I mean, the unbalance, just we return back again for the first assumption from here. If you notice, we said that this is the balance system, okay? But when we have unbalanced system, then we don't consider this one as a 0. It doesn't provide something, especially when you're programming the MATLAB. You just can say that, okay, this is I1, I2, I3, and when you provide the input, it calculated based on that one. So it doesn't provide something, but you cannot assume that this is the 0.
Only it is 0 in unbalanced.
Yes, yeah. Because I mean, if you don't understand the balance system, then unbalance is more complicated, and the equation will be 10 times more. But when you go from the actually coding the controller by MATLAB, because you just write it and see the result, so it is not that much hard. But the important thing is that when you make the programming, you should at least have an idea about that, what is the shape of the signal you are expecting. So for example, in my case, when I'm using the simulation, I don't use PLL. I don't like it. I just calculate the alpha beta and based on that get the inverse tangent and then said that if the VD is in direction of the V reference, VQ is equal to 0. And then I put a scope. And if VD is DC and VQ is equal to 0, I said that, okay, now nobody can say that this is a problem because it is impossible. If you program it the wrong way, the Q will be 0. So then immediately when run the actually code, I see actually the VQ is 0. It means that up to here my simulation is correct. So you should have actually some idea about the stages that you are proceeding. And the worst or biggest mistake is happening, especially for the PhD student. They start at the beginning. They are going to close the simulation and run it and to see that it works well or not. No, it is the biggest mistake. So you should be like a doctor. When doctor, someone has a good experience, you go there and see that, okay, I have a headache. Then they like a less experienced doctor said that, okay, headache can happening because of the flu, can happening because of the corona, can happening because of the, I don't know, sign problem, can happening because of someone hit your head. And then let's try, okay, go to take a photo of actually your, I don't know, what do you say? Then you see that, okay, your head is not broken, so it is not. Then have a corona test, then it is not negative, so it is not good. Also, again, go do this one. But the experience, actually, doctor said, okay, so let me touch your, okay, so it is because of this, and go do this one. Okay, so you should be like this one, because the expectation from you is that at the end of your study, you should find the solution based on the result you see. And if, for example, you see the graph is not, the injected current is not actually pure sinusoidal, you can easily say that, okay, it can be because of the, I don't know, DC voltage is not regulated, or switching frequency is not tuned well, or the filter is not designed well. So these three factors can be the reason for this THD. That's all. So for this case, the expectation from you is that, you know, when you make the simulation, at least you don't close your eyes and say, okay, so finalize, and then it doesn't work. I mean, the chance is then less than 1% if you make a simulation and then say that it works very well. Even less than 1%. Do you agree, guys? Okay, good. So, now we get back again to DQ. So we have this equation. At the end of the story, we have L di to dt Ri plus dnv dc equal to Vd in dq0 reference, actually, transfer function. So this is for phase 1. For phase 2, we have also the same scenario, but with 120-degree phase shift. So again, we follow the same, and when we actually repeat the same procedure, we reach to this equation. But the only difference from phase 1 and phase 2 is that in phase 2, we follow this one, cosine omega t minus 120 degree minus, I mean, it has the phase shift. So for this, the new equation will be obtained almost similar, but with 120 degree phase shift from the phase A. So at the end of the story, you have this equation, L di to dt plus Ri plus dn phase 2 times to Vdc equal to V grid in phase B, or second phase. And in phase 3, we follow this part, cosine omega t plus 2 pi over 3 times to Vd minus sine omega t plus 2 pi over omega t times to Vq and plus U0. So by this, we reach to this equation. Okay? So it seems a lots of equation, but you know, we are not mathematician, we are engineer, and then we are very smart, intelligent person that that can easily calculate this one, but we have a software, so easily we can use the software and calculate this one. So we don't need to memorize this one. So at the end, if you have something similar in your exam, it will be very probably a stupid question in the exam that the expectation was that you memorize the Park transformation. I mean, I'm teaching this course or using this Park transformation several years, but still I cannot memorize it. Yeah. Udaya, can you memorize it? Okay. So, you want to close it? Now let's conclude this part and then we, okay. So now we get back, actually we have 3 phases, and in phase we have phase 1, phase 2, phase 3, we transfer from ABC to ODQ or DQ0. So by this assumption, we make the summation of the actually 3 equations. Phase 1, equation 14. phase 2 equation 15, phase 3 equation 16. So by summing this, you can see that, at the end we have L dId to dt minus L omega iq plus RId plus dN dV dc minus Vd times 2 cosine omega t minus 2 p over 3 plus cosine omega t plus 2 pi over 3. Okay? And then in the second part, L di to dt in q axis. It is in d axis, is in q axis times 2 sine, and at the end also for the homopolar value we have this. So if we get back to this, it is equal to 0. When does it happening? It's happening when this value is equal to 0, this value equal to 0, this value equal to 0. So L di to dt minus L omega iq plus Ri d plus dN dV dc minus Vd equal to 0, this part. And this part also equal to 0, and this part equal to 0. So the summation of these three phases will be equal to 0. Is it clear up to here? So what is happening? You see this equation change from ABC to DQ. So we transferred from the ABC operating condition to DQ condition. So if we get back and see a little bit with more detail, we see that we have L dId to dt minus L omega iq plus Rid plus we see that all actually components here are from D except this part. And we have also the same, all components are Q except this part. And we call it coupling, point of this system. So it, cross coupling. And is it good or bad? It's bad. Why? So, for example, we are going to control a converter. And I'm saying that I'm going to inject 10 kilowatt active power. And later see that active power can be modeled by ID, reactive power can be modeled by IQ. So it means that I'm going to inject 10 or 20 kilowatt active power in time t equal to 3 seconds. And then, so when we have this power increment, in fact, we changed the ID, but this ID appeared in I here in the Q axis. But Q axis also referred to the reactive power. So you see that, reactive power is 0, 0, but when you have this, we have a spike here. Okay? So for this case, we should remove or find a solution to remove this part, and we say that decoupling. Okay? So, does anybody has any idea about this? How we make the decoupling? Or are you interested to know how we make the decoupling? Yes? We see later, okay? So I'm now getting tired, so we can take a rest and then follow with the Udaya afternoon. Coupling, continue on what? Tomorrow? Okay, tomorrow. Yes. But we will get back again to a little bit explain to other people that were absent tomorrow. Yeah.
Can we wait for lunch? We'll wait for the lunch, and the lunch can be served in the ground, the same location. We can collect it. In the afternoon session, I'm going to handle the session for the technologies for the renewable energy.
Yeah. But before leave, is it actually understandable or not? If you have some problem, tell me, okay? Because this is very important, and end of the we follow the same actually direction up to end of the next week. So if you don't understand these things, just tell me. But I'm saying that you are very intelligent and you can understand it very well. Yeah.
Yeah. No response?
Good morning.
Have you got proper sleep?
Yes.
Had your breakfast or not? But they are saying that you have not taken the breakfast. They are feeling sad if you won't take the breakfast.
Yeah.
Okay? We are paying for it. Okay? You are supposed to take the breakfast. Hmm? So once again, good morning to one and all. Yeah, fine. We'll continue the session with our eminent faculty, Professor Edris. Today's topic is on the operation and control of grid-connected power converter. Continuation of the yesterday's thing that we will have the session with the Professor Edris. Yeah. Over to you.
So thank you, Udaya. So good morning, everybody. Before we start, just briefly say what happened yesterday. And today we are continuing our discussion regarding the control of the grid-connected converter. So yesterday we discussed about the different types of the conversion system. So they said that classification of the power converters, but this is not correct. The correct is that conversion system. So we said that we have the grid following, grid forming, and grid supporting system. So grid following, just follow the voltage and frequency of the system and then provide the power from generation to the load side or to the grid. So basically the idea is that we support or we inject the maximum power from generation to consumption. So just a simple example is that, assuming that you are the owner of the, 1 hectare land, and you are going to install the PV panel there, and then based on the forecast of the power generation, the PV radiation, you can see that, okay, based on that much radiation, I'm assuming that in 1 hectare land, I can provide 5 megawatt power. Then you talk with the distribution company, and distribution company actually, you said that, I can provide that much power. For example, during the early morning, the profile will be 3 megawatt. In between 11 to 4 p.m. will be 5 megawatt, and between 4 to 8 it will be again 2 megawatt. Okay, so this is my profile that I can provide for you, and you provide everything based on the day, but assuming that this is because of the forecast from the previous year, there is some possibility that the weather today is different. From today is raining, but last year was sunny, so our forecast is not correct. So what is happening then? You should buy the actually storage devices to just make sure that what you promised is completely correct and you meet it, because based on what you promised, distribution company also promised to the load side. So for this type of system, we normally use the grid forming converter, because we are somehow committed to provide the power to the grid. And if grid is, some problem is happening, we don't care for that one. We are not responsible for that one. We are responsible to provide the power for the grid. And the main idea is to provide the maximum active power. And we mentioned that, for example, in Atacama Desert, they said that each unit of the generator was 1 megawatt active power and 50 kilowatt reactive power. So, so the reactive power is uh, because of the keeping the voltage stability in the system. But the main idea is transfer the active power from the generation to load center. But for the grid forming, we provide the, we control the converter in a way that it reacts as a voltage source. So it provides the reference voltage and frequency. So by this, if you are somewhere isolated from the power grid, you can react as a grid. And then the other conversion system can be also connected to that one and provide the electricity for the power grid, for the load. So just simple example is that you are actually living somewhere which have no access to transmission and distribution line. Then you need to use the grid forming technology to provide the electricity from wind, solar, or whatever you have, and support your isolated loads. You have grid supporting. Grid supporting is basically following the actually instantaneous angle of the grid. So basically, it's coming from the voltage of the grid and frequency. So by this, we can actually, the main idea is to support or regulate the voltage and frequency in the grid. So this is very important to support the stability of the grid. So if we have actually one converter which we are expecting to inject, for example, 8 kilowatt and 8 kilowatt active power and 6 kilowatt ampere reactive, then when the voltage drop, we can increase the reactive power, and if the frequency drop, we can increase the value of the active power. So make the somehow support the voltage and frequency stability of the grid. Any questions so far? So this is quite probably clear for you nowadays. I mean, I know that you need it probably, but just return back again to the thesis. So this is the just the model that we can consider. This type of grid forming converter is working like a current source, and the grid following work like a voltage source. So this is also grid supporting, so it can work as a grid as a voltage source or current source, both operating condition. So this is also some more detail how we can actually reach from the actually this type of converter to support the grid. Just there are nothing new. And then we discuss about the Park transformation. So and Clark, so we noticed that this is just the matrix we are using to transfer from 3 dimension to 2 dimension. And the idea is that, you know, in ABC, the components, voltage, currents, they are variable, but when we transfer to DQ, then it will be DC. So just a simple example here. If you go, you see that, you know, it changed based on the theta, value of the theta, and the value of D and Q also are not constant. So it can go from 0 to some to reference voltage, or here also Q can go also from 0 to reference value. So this is a balance between the D and Q. So basically the equation we have is V reference is equal to VD2 plus VQ2. So you can see from here. So this is our reference value. I mean, this is VD, this is VQ. We have the 90 degree. So when we provide the reference value, it is a part of this equation. So as much as the VD increase, VQ reduce. And when we increase the VQ, VD reduce. But this equation is equal to reference voltage and is a constant value. So the main idea and important things is that when we transfer from ABC to DQ, the fundamental frequency are actually DC value. So by this assumption, we can separate the fundamental frequency from the harmonic, and then compensation and control will be much more easier for us. This is the main reason. Yes? VQ0, why? Okay, but why it is 0? Why?
That's my question.
Oh, this is your question. Okay. Okay. This is VA, yeah? Okay, this is B, and this is VC. Do you agree? So we transfer it to VD. So this is XY, okay? So we transfer it to VD and VQ. So VQ. And this is a 90 degree between them. Yeah? And this is also theta. So theta is the instantaneous angle of the grid. Okay? So if we consider the voltage of the grid like this, so theta can be between 0 to 2 pi. Is it clear? Okay. I will ask you again to come here to explain. So pay attention to this one. So this is theta. The theta can change from 0 to, so I think when I get in close to this amplifier, this type of noise happening. But okay. So then we also had the alpha beta. So this is, we said that, V alpha, V beta are sinusoidal. It started from 0 to 90 degree. If you go to this one, you see alpha and beta. It started, but by 90 degree shifts here, okay? So if you look at here, then it can be alpha axis, it can be beta, okay? So if you consider V alpha and V beta, do you agree by this? So it means that VD is equal to V reference. Yeah? So it means that if we consider theta equal to tangent inverse V beta to V alpha, then V reference will be equal to VD. Okay? So here we mention also V reference VD2 plus VQ2 is equal to VD. What is the conclusion? VQ is 0. So, if we consider theta by this, in fact, we consider the theta equal to tangent inverse V beta to V alpha, then the direction of VD will be in direction of V reference. Then VQ will be equal to 0. Because if we get theta like this, then it will be like this. The reference will be this. But when you consider theta equal to tangent inverse V beta over V alpha, in fact, the direction of the V reference will be equal to V reference will be in direction of VD. So all V reference will be equal to VD, and VQ will be equal to 0. You can do something else by tuning the PLL, okay? But my advice is that, you know, if you go by this direction, then the calculation will be much more easier for you.
What if we just make opposite, for example, VD 0 and VQ as a bigger?
I mean, it's like you're going to eat the lunch, take the spoon, and eat this one or eat this one, okay? So you can actually say that I get the theta by this one, VQ, okay? Theta, so it's like a tangent inverse V beta to V alpha plus 90 degree. If we consider by this, then VD is equal to, VD is equal to 0. But what is the benefit? It's like a mathematical equation. You can consider whatever you want. But basically, if you consider this one in your calculation, you easily can neglect the VQ, and VD will be your reference value. Yes.
So here VD and VQ are decoupled.
Yes. No. They are coupled, but later you can actually decouple it. Okay. But here you see, yeah, they are actually 90 degree different.
Theta is 90 degree.
Yeah.
So can we get the similar condition in Planck transformation?
What? Can you repeat again?
Can we get the similar situation
Yeah.
using Planck transformation between V alpha and V?
I mean, when you're going to talk about the Clark transformation, there is one benefit which alpha axis and the beta axis, they are always decoupled. Okay? But then you have the sinusoidal value. And making a reference for the harmonic makes a little bit challenging for you. You cannot separate it. So basically, it is better that you go first to Park and then jump to Clark to actually to separate the alpha, the alpha from beta. But I mean, there are different methods you can use it. But I mean, most straightforward way is with D and Q. Because this decoupling is not that much complicated. We see that one. Yeah. But if you have a smart solution based on the alpha beta, so it is recommended to go and solve your problem based on the alpha beta. Yeah.
For the decoupling, active power and reactive power.
For the decoupling, basically, yeah, the reason is that you just separate the impacts of active power from to reactive power and reactive power on active power.
Can you do that easily in Planck transformation?
Let's see.
Why? Because
Let's see.
mostly MPC techniques.
You say that Clark transformation. Clark, they don't have a coupling part. They are decoupled. But Park, they have the coupling part. So the weakness of the Park comparison with the Clark is that in Park transformation, when you go to the control of the converter, the coupling will be appeared, but in Clark you don't have it. But there are also some weakness from the Park also. Clark also. Yeah.
Without making VQ is equal to 0, is it possible to synchronize with the grid?
Repeat again slowly.
Without taking VQ is equal to 0 reference,
Hmm?
is it possible to get synchronized with the grid?
Yeah, of course. Yeah, there are some other. This is not the only method. Yeah, but I mean, basically for example, alpha beta, you can go from the positive negative sequence, and then you play with the actually negative part with the positive part and separate it and create the reference based on that one and compensate it. There are several methods, but if we get back, probably one of the most easiest way use the Park transformation, and then you have the flexibility to apply for the different application. But I'm saying that again, that Clark transformation has some benefit in comparison with the Park, but when we are going to just, for example, just grid connected mode or grid forming mode, grid following mode, they are different actually aspects. So if I'm going to say regarding the grid forming, you are working like somehow grid following. I'm sorry. You are working like a current source, and you need just to inject. Okay, you are not going to compensate. So probably Clark can work better. Yeah, but when you go to the grid connected mode, then it is much more better to consider the Park, because you can separate the frequency with the fundamental frequency with the harmonic frequency, and then compensation will be much more easier. Yeah. But later we see that decoupling is not that much complicated, at least in the paper. Okay. Any other question?
One more thing. You said one more, suppose you are going to make VD is equal to 0,
Mm-hmm.
and VQ take as a reference. V reference as
No,
VQ.
VD is not, VQ is equal to 0.
In other way, suppose
Okay,
I
yeah.
make it like this,
Okay.
but the direction of the current is reverses.
No.
Read
No,
as same.
no. Let's see. I will discuss about this part in the lecture. But the direction of the converter cannot change if you see that one. It's not actually referred to the current injection. So let's see. I mean, I will explain that one. But now we see that we have the Park and Clark transformation. Then we can actually, by Park, we can transfer from the sinusoidal to DC value. So later, if you are going to make the simulation, if you consider this one, so V alpha theta based on this equation, then D will be equal to V reference, VQ will be 0. So when you run the simulation and see that VQ is 0, it means that your simulation up to here is working well. It is something also I consider. So then we talk about the grid connected converter. We see that we have the converter based on the sources and the grid. We have actually filter after the converter. We have the grid with the impedance of the grid and nonlinear loads. So we said the leg voltage V1M, V2M, V3M is equal to phase voltage plus voltage of common mode. So by this assumption, we reach that VNM, or voltage of common mode, is equal to 3 voltage of the actually 3 legs plus over 3. So then we provide the dynamic model of the system. Now if I ask Costa, can you actually prepare this equation easily?
Yes,
Okay, that's enough. I trust you. So we noticed that it seems very complicated, but it was like a piece of cake for you. Am I right? Does anybody can say no? Yeah, okay, good. Arya is not here, yeah? I saw him during the... No, he's not here, yeah? Okay, good. He was disappointed about this technology. Then we actually going to actually talk about the dynamic model. When we are talking about the dynamic model, what was the meaning of dynamic? Dynamic is coming from changes. It's something changing. So now we just transfer the equation based or provide the equation based on di to dt and then here. And then replace the voltage of the leg with the switching state function of the leg 1 times to VDC, S1 times to VDC, and for the common mode we also have the previous equation. So by this we can just replace the V1 M, V2 M, V3 N over to 3, and for each V1 M, V2 M, V3 M we put S1 VDC, S2 VDC, S3 VDC. So by this we can reach to this equation and then just transfer the two switching function, and we call it switching state function by this. Okay, so if we provide between 1 to 3 for D N1, D N2, D N3, we have such a matrix which provide the actually different switching state function for the each leg, and it shows that the operation of the one phase is subjected to the operation of the other phase also. So by this we have the dynamic model of the system with the three phase in this matrix, and we have the balance system. So in balance system I1, I2, I3 is equal to 0, and V1 plus V2 plus V3 is equal to 0. And based on the matrix we provided for the D switching state function, we have also such a dn1, d2, n2, dn3 equal to 0. So by this we can actually provide this equation by removing the third part. If we have one phase and second phase, then we have also a third phase by this. So now we discuss about the how we have the model of the system in ABC. Now we transferred from ABC to DQ. So we have three phases, and this is the equation we discussed for the park. And based on that, the parameter we had in D and Q and 0 can be calculated by this. So for example, for phase 1 is any parameter, any variable in in d axis times to cosine omega t. So it's coming from here, u1 cosine omega t to ud minus sine omega t uq plus u0. So if we get back to this, L is a constant, R is a constant, VDC is a constant, but we should consider di to dt, I k, and also dn k and v k, and transfer from ABC to DQ. So by this assumption, we actually follow these three equations, and just for example, di to dt, we get the derivative of this equation and just replace, instead of u, we replaced I. So di to dt will be did to dt cosine omega t minus omega id sine omega t for the first part. And for the second part, diq to dt sine omega t minus omega iq cosine omega t. And for the third part, di0 to dt. And for the second part, we have ri. I is id cosine omega t minus iq sine omega t plus I0. And for the next part, dn. So we just change the dn from d and q part. And for v1, vd cosine omega t minus vq sine omega t plus v0. Is it 100% clear? Does anybody can say I need more explanation or something is not? I mean, this is the switching in leg 1, leg 2, leg 3, okay? So it can be, when we say that S1, it doesn't mean that this is this one, okay? It is this one or this one. It's a leg 1, okay? So one of them can be on, one of them can be off, and you have, based on that, you can have the actually output voltage. It can be either 0 or VDC.
We will take either 0 or 1
VDC,
in that case,
yes, yeah.
in the next slide. Yes, sir. S1, S2, S3.
S1. Mm-hmm.
S2 and S3 are off for example. So 1 0 0.
Mm-hmm. 100 means that it's first on, off, 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 on, like this. Yeah. It's clear.
We will take 1 0 0.
100.
If S1 is on.
You're talking about this. So is, I mean, this is function. This is not actually binary number. This dn is a function. And if you get back to the equation, you see that dn, which define this one, is a function of the dynamic system. Okay? It's not the switching.
In the very first equation,
It's like a duty cycle for the converter. So it's not like a binary number on, off, on, off. No, it's not that one.
in the very first equation, 1 by L bracket S1. So what we are supposed to take?
No, S1 is the switch. It can be actually S1 because, you know, when we said that S1, okay, so assuming in this model, we consider S1. So we get back here, S1. So if this is on, what is the value of this? 0, okay? But because I mentioned S1, S2, S3 means this leg 1, leg 2, leg 3. We cannot say that S1 is here and S2 is here. No. So I understand, but yesterday I also emphasized that don't make the mistake because this is the leg 1. The switching state function in leg 1, switching state function in leg 2, and in leg 3. Okay? So, but in power electronic, we consider the order by this S1, S3, S5, S6, S2, S4, S6. There are some reason. Okay? But accept this one by this, you know, when we are saying S2 means that switching state function in leg 2, S3 in leg 3. Okay? If you want, I can actually easily modify it, but this is, I think, clear. So, any other questions so far? Good. So when you make the simulation, please, I mean, you never reach to this point because we normally go through the dynamic model and provide the duty cycle. But basically, you should understand that the S1, S2, S3 in this equation is switching state function in leg 1, leg 2, leg 3, and it's clear because when we say that I2 is passing through the phase 2, and then phase 2 is connected to the switching state function in here. This is the, so is this one or this one. So it doesn't make sense that this is V2, V2M is equal to 1 or 0 to this one. So it's a leg 1. Okay. But if not clear, just later tell me and I explain more. So we discuss about here and switching function and then dynamic model of the system and then transfer it to dq, and reach to this equation, which if you are going to meet, I mean this dynamic model in dq, d-axis, in q-axis, and 0-axis should be equal to 0. So then we have this parameter, we call it, because we are in d-axis, 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 but we have also q component. So this q component, we call it coupling term, and we have also this coupling term. They make noise for the other system. So it means that assuming that you are going to inject active power to the power grid. So this is your P, and this is your Q, P. So assuming that here we have a load which we need to inject 10 kilowatt active power, but the reactive power is equal to 0. Okay? So when we switch to active power, then this coupling provides a spike here, like this. Zero, 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 and then we have a spike here, and then again. And this spike to the Q is from this term. Okay? So this is why we need to somehow remove this part from the control loop. And then later we see that it easily can be actually removed. So up to here is clear? Does anybody can say, I didn't get it, it makes my life hard, you're not actually explaining easy, so no? So if I ask a question, it means that all of you knows that what is the answer, yeah? Okay. Nobody say, Professor, anything. Then you don't know they agree or disagree. Yeah. And the problem is that all of them had a very good breakfast. Yeah. Okay. Anyway. One time again, I'm saying that I'm here as a lecturer. My responsibility is to teach you. I'm not an examiner. I'm not going to punish you. And if you don't ask me now, later I will not answer to you by email. Okay, so you ask me, and it's good that contribute in the class. So now we have three equations. So in balanced system, we know that this is actually happening. I1, 2, 3 is equal to 0. V1, 2, 3 is 0. And also based on the equation, we had the same. So by replacing by this, we can see that if we have two-phase, if we have the balanced system, then the homopolar value will be, we call it this 0, is homopolar value will be equal to 0. So the final equation will be this. So it means that we change from the ABC model to the dynamic model of the system, transfer from ABC to ODQ or to DQ. So if we get back and ask the question that, okay, you did it, you spend lots of time and transfer this fund to DQ. What is the benefit? Now Rakesh is going to say that what is the benefit? So now is the problem when you don't ask the question. Okay? any, let me, Abe, what is the benefit that we did it?
We minimize the number of variables for calculation.
He's very actually a smart guy. You know? Okay, so he answered, okay, it's true. We minimize the number of the variables, but what is the benefit? Control is easier. So what is the benefit? Control is easier.
Control is easy.
Yeah, exactly. He's very smart guy. Yeah, okay. So when we transfer from ABC to DQ, in fact, fundamental frequency become a DC, and then we can separate the components from the fundamental frequency and make our control easier. Okay? This is one benefit. So now we get back again to discuss about the value of the theta. So we have different actually way to calculate the theta. So anyway, you choose, the answer will be the same. But for me, I normally go from the theta based on this equation. And if you open the actually MATLAB with the PLL, you see that the source of the MATLAB in PLL in the MATLAB is also based on this equation. But you can actually tune it based on different value of the theta. So theta can be actually based on this equation or something else. But anyway, so we have V alpha, V beta. I just 10 minutes ago I shown you that it started from the 0 and they have 90 degree alpha from the beta, and we have also D and Q axis. They have also 90 degree. So by this assumption, if we consider theta equal to V beta over to V alpha, then it means that the direction of the VD is equal to direction of the reference value, because reference value is V alpha to V beta 2 is V reference value, which is equal to VD. So by this assumption, our VQ will be equal to 0. So if we get back to the previous equation, we can simply replace here equal to 0. And as Abe mentioned, we optimize the number of the variables in our equation. And so by this, the equation transfer from this to this, okay? So now we have actually this equation. Now we said that, we are going to design a controller, and the controller, for this, we need to proceed the dynamic model of the system. And as all of you know that what is the benefit of this dynamic Navina. So what is the benefit? Why do we need the dynamic model of the system to design a controller? Yeah, exactly. I didn't hear, but I feel that you mentioned that we have the model, so we are going to see that what is the generation, what is the consumption interface, and what is the consumption or load side. If we have the dynamic of model, then we can exactly. Thank you, Nabina. Okay, so so now if we get back to yesterday, we discussed about the dynamic model of the system. We have an equation which any